During the follow-up, that is today and tomorrow, August follow-up, I'm going to talk primarily about rotational motion. Okay. It's really, I'm glad it's funny.
Her reaction.
Oh, was it good or bad? Rotational motion. And then we will build on this throughout the year when we meet on a monthly basis. Okay. So I thought I would start by giving you a quiz. Okay? And I'm not going to collect the quiz. You're going to hold on, but I want you to take the quiz, and hopefully at the end of this, you'll have a better understanding, and maybe you could look at your quiz again and see how you did. Okay? So this is a little quiz on rotational motion, like pre-quiz. You may have to guess on a few things, which is okay. Okay, you don't have to look it up. Just make your best estimate. You can talk about it with your neighbor if you like. You're not going to get a grade. Way over here by yourself.
She's coming.
You can see by looking at the quiz the topics we'll be covering. All right, rolling motion, torque, center of gravity. And at the end, maybe tomorrow, or if not tomorrow, then certainly our first get-together for the monthly meeting, we'll talk about each of these questions, and just you could bring your quiz with you to see how you made out, or hopefully, even if you were to take it again, maybe you would do a little bit better than you did, because you probably made some guesses in some of the questions today, right? Yeah, okay. So rolling motion in physics is a specific topic because up to this point, what I have spoken of this, during Immaculata week was really linear motion, right? Either motion along a line, such as a car moving, or trajectories, motion in two dimensions, such as our friend Einstein jumping out of the building, or even the motion of the bullet. And in all those cases, we assumed that the object was a point. All right? And then we used our equations to do certain calculations describing the motion. But in the back of our mind, we may not have thought about it, we were looking at them as a point. That is, we didn't think about, we didn't even discuss, when Einstein jumped out of the hotel. Anyone remember the name of the hotel? Hotel Odyssey? Yeah. We didn't talk about, he didn't come down as a ball. He probably came down turning, right? There was some rotation to the body, and that, in fact, would have affected his trajectory. So we're going to now look at that aspect of motion, that is what happens when something is rolling. Could you open a couple of windows back there, please, just to cool things down a little? You don't have to open them all, but... Is anyone cold? No? Okay. Okay. Well, we'll cool you off so you can wake up. Okay. So, rolling motion, right? This is when we... Oh, I couldn't remember what I did. I thought they were going to go one after another. I guess I have to click each one. Okay. So, we'll start very simple with just circular motion and put some descriptions and definitions of what is circular motion. And then we'll add the extended body, something that has inertia, something that has length, width, and depth, and how that affects the motion of an object. We'll talk about how we get an object rotating through the use of torque. We'll talk a little bit about center of mass and the difference between center of mass and center of gravity. And then finally, if we get the chance, we'll go all the way into centripetal force. Also, what keeps something actually in circular motion, centripetal force. And then later this year, when we get together for our monthly meetings, we'll cover angular momentum, right, momentum of rotation, and conservation of angular momentum, and a few other topics we'll cover also. All my slides are up on the wiki space in case you need them. Circular motion. Okay. If we take a look at a DVD or a CD, we watch it as we turn it on, it begins to spin or begins to rotate quite quickly. The whole disc is rotating at a specific number of revolutions per second. I mean, you can picture that occurring. The tire on your car all rotate at so many revolutions per second. But there is a relationship between how fast each point on an object that's rotating is actually moving. Right? What is the speed of each point? And basically, even though the whole CD is rotating maybe at some constant angular velocity, right, depending on where you are relative to the axis of rotation really determines how fast you're going to be going. There's no question that you put something at this point 4, that since this is all moving together, point 4 has to cover a lot more distance than point 1. So point 1's velocity, linear velocity, is going to be a lot faster than point 1, even though they all have the same angular velocity. That is, they're all rotating the same number of times each second. And we're going to look at what circular motion is and the relationship between circular motion, the rotation of the CD, and linear motion of different points on the CD. Right? So we'll look at that kind of relationship. And that has a big impact on a lot of everyday things. And I have a couple of activities for you to do that shows where this actually applies. Just as a little review, last year, if you were with me last year, or even I think during Immaculata week, I talked a little bit about how we define linear motion. I mentioned that we talk about speed and velocity. I bring this up here only because I'm going to use the term speed and velocity interchangeable today. The difference is, of course, speed just tells us how fast you're going, and velocity tells you also the direction you're going in. Okay. Velocity is a vector, and we're going to use the little arrow, the little vector arrow, to give us an understanding of whether a velocity is large with a large arrow or a small velocity with a small arrow, and then also which direction something is moving by the direction of the arrow. In linear motion, now if you teach physics or maybe some science, we usually use a variable for a distance, right? I often use x. I don't know if some of you may use d for distance. Sometimes it's L for length, also a measure of distance. So these are what we're used to, using parts of the alphabet to indicate a variable. We use v for velocity. We're going to use different terminology for rotational motion. Okay. So x or d for linear motion. And so for rotational motion, we're going to use how fast something actually revolves. Right? And we do that by taking an object that may be moving in a circle like this. And I can actually put it on the xy plane, just as we had the concept of using an xy plane with someone jumping out of the hotel. That is, that person had a velocity in the x direction because he was running. And he also began to acquire a velocity in the y direction because he began to fall under acceleration due to gravity. So we were talking about x and y there. Here, we're going to talk about angular displacement. Okay, so the displacement is not in the x and y plane, but it's going to be the rotation about a specific axis. In this case, it's very easy to find an axis of rotation here. We know it's the center of the disk. Sometimes we're going to have objects where you can have multiple axes of rotations, and we'll have an opportunity for you to find some of them later on. So again, instead of displacement being x or y, we're going to talk about displacement in terms of angles. Right? So from here to here is how much? How many degrees? 90 degrees, right? And then if I were to rotate it this much, 180. Okay, so we're used to using 360 degrees, right, all the way around. Only when we do a lot of our work, we run into trouble using degrees, and we end up using radians instead. And this is the terminology that is one revolution around, one rotation, okay, is 360 degrees. It's also equal to something we call 2 pi radians. And radians is a unitless value. It falls out a lot of times. Okay. So we know this is 1 pi, halfway around. This is 2 pi. Right? 1 pi, 2 pi. Okay. And angular displacement is going to be, how much we rotated from some initial point, some initial angle, theta, to some final point. And then you have your difference in theta. So maybe you're moving from 20 degrees to 80 degrees or 70 degrees, or you have a delta theta of 50 degrees. Okay? So we can see it in degrees. We're not going to really use degrees, but we're going to use this conversion right here. There's also an agreed upon concept of what happens if we're rotating clockwise or counterclockwise. Anything that rotates clockwise, we give it a negative value, just by convention. Anything that rotates counterclockwise, we give it a positive value. Okay. So while we use x or d for linear displacement, for angular displacement, we use theta. So once we have a definition of displacement, we next have to go into angular velocity. How fast does this rotate? And it all rotates together. Every point on it rotates together. Every point has the same angular velocity, that is change in theta over change in time. Let's see. So let me just put down here, this is theta is angular displacement. This isn't writing so well. And the next term we have is omega, right? The Greek omega. And that's called angular velocity. All these ought to be thrown out. So that's the speed, that's the number of rotations that's occurring over a period of time. It's so many revolutions per hour. You look at the Earth revolving around the sun, it's so many revolutions per year. What's actually 1 year once around. But usually we talk about not revolutions, but radians per second. Radians per second, because we're measuring angular displacement in radians, right? 2 pi radians is 1 revolution. Okay. So it's a change in radians over change in time, and we use seconds for the SI units. Again, when something is rotating, every part rotates at the same angular speed. Right? The omega is the same for every point here. However, any individual point has a different linear speed. And it depends on how far it is from the axis of rotation. So the distance traveled by a point on a rotating object divided by time, right? So the distance traveled by this little bug divided by the time that it travels. So the distance would be going around in a circle. Right? That circle, that circumference would be 2 pi r. Right? The distance is r, 2 pi r. We call that its tangential speed. And the reason we call it tangential, you're going to see in a minute. And it has the symbol v because it's a linear value. It's not the rotational value, but it's how fast it's going in that particular instant. So v, I think we need a whole new box of these. Just keep going through them. tangential speed. So these Greek letters are angular, and the alphanumeric letters are for linear. And as we've noted before, anything that's closer to the axis of rotation is going to go slower as this goes around. Anything out here is going to go faster. It has a greater linear velocity. Now there's a relationship between this bug's linear speed and its distance from the radius. Okay? And the relationship looks something like this. Velocity of an object is equal to the radius times the angular velocity of how quickly something is rotating. Okay, so this is velocity is equal to r times the angular velocity. Yeah. Okay. So that means if you look at the Earth, and here we are, right here. Here we are at Immaculata. Okay. The Earth rotates at a very specific angular velocity. Right? It rotates once around every day. That's its angular velocity. Right? One revolution is 2 pi radians. Right? So its displacement is 2 pi radians, and every day is, I don't know how many seconds, it's 24 hours in a day and 3,600 seconds in an hour, whatever that comes out to. Right? So that's a very specific angular speed for the Earth. However, where you are on the Earth determines how fast you're actually moving through space. If you're on the equator, you are so here's the axis of rotation that goes through the center, right? You are pretty far from that center of you're the furthest away from the axis of rotation that you can be and still be on the Earth when you're on the equator. Okay? So you're going a lot faster out here than you would be if you were up at the Arctic Circle, where you're a lot closer to the axis of rotation going through the center of the Earth. So everyone's moving at a different speed. And it's also shown, first of all, you'll notice that this velocity, how fast you're going, is indicated by this velocity vector. It's much larger than up here because you're going a lot faster. And you'll also notice that it's tangent to the surface of the Earth. Right? Makes a 90 degrees if you were to go to the axis of rotation. Right? That's why it's called tangential speed. Now you don't know you're going faster down. In fact, I visited a friend who lives in Quito, Ecuador, a couple of years ago, and she brought me to the equator because the equator goes right through Ecuador. You get to stand right at the equator, north and south, and the whole thing. And I realized that I was probably going the fastest I'll ever go. But I could feel it, obviously, because the whole atmosphere is going with us, right? So it's not like the wind is going past me at 90,000 miles an hour or something. But you could calculate what your speed is. If you knew the radius of the Earth, you could look it up very simply, right? We know that the actual angular velocity of the Earth, omega, boy, oh boy, I wonder what's wrong with these. Omega is equal to 2 pi radians, 1 revolution per one day. And you just multiply that by 1 day has 24 hours. And 1 hour has 3,600 seconds. So whatever that value is would give you the number of radians per second. Okay. And then you multiply it by the radius. That is how far you are from the center of the Earth, and that would tell you how fast your linear speed is. Okay. Does everyone bring a calculator? What? You come to physics without a calculator? You have a calculator? Okay. All right. So let's do one quick calculation. before we go on to our activity. So here's an example. Okay. The relationship between tangential speed, the radial distance, the distance from the radius or the axis of rotation, and the rotational speed, or rotational speed and angular velocity are the same terminology. And the question is, compare the tangential speed of a person at 1 meter from the axis of rotation, let's say this guy here. How fast is he going with a person at 4 meters, the guy out here? So each one would be going at a different velocity, even though they're rotating at the same speed. Okay. They all have the same rotation. The rotational speed is 2 pi radians per second. So what that means is 2 pi is 1 revolution. So this is going around 1 revolution per second. So what would be v for each one of those people? And all you would have to do is multiply the radius, which is the first person is at 1 meter, times 2 pi radians per second. The second person, v, would be equal to 4 times 2 pi radians per second. That would give you the difference between their two linear speeds.
And the radians just drop?
The radians are unitless, they just drop, yes. So what would the speed comes out in meters per second actually? So you have to multiply 1 times 2 pi. So if you have a calculator, maybe you know in your head what 2 pi roughly would be. You can do a little rounding. Anyone have any answers you want to share?
I have no.
Okay.
I got 6.28, I got 25.12.
That's exactly right.
Yeah.
Very good. No trick. It's simply 1 meter would be the first guy at 1 meter times 2 pi. Pi is like 3.14 times 2, which is 6.28. So it's 1 times 6.28. So that person is going 6 meters per second. The second one is at 4 meters. He's further out, further from the axis of rotation. They're all rotating at the same speed, but their linear velocity is different. So it would be 4 meters times 2 pi. Again, pi is 3.14 times 2, which is 6.28, times 4, about 25 meters per second. So the guy out here obviously is moving a lot faster. You've experienced this probably. Have you ever done any ice skating where you whip around or something? Ever done that?
Yep.
As a child? As an adult? You make sure you're not on the end, right?
Yeah.
The whip. Okay. So, we know the guy on the end's going faster, right, on the edge, because they're further from the axis of rotation. Okay. What causes that increase in speed? Oh, first of all, you notice that at any one point, right, as this thing is rotating, so if his speed is tangential, I can use a little arrow to show which way the speed, if he's moving, okay, it's rotating this way. If I pick it up, it's rotating clockwise, so it's negative, okay? And the speed of this guy here, I could show by like a velocity vector like this, right? And this guy's velocity vector would be tangential to his motion of rotation, and it'd be a lot smaller. It'd be like this. And then as it rotates around, now my little ladybug is over here, and that's his velocity vector there. Okay, so the direction is always changing. The speed is the same. He has the same speed, 25 meters per second or whatever it is. But the direction that he's moving is continuously changing because he's moving in a circle. So its velocity is changing, even though it's moving at the same speed. Okay. And in circular motion, it looks something like this. So have your bug, and at each point, if I were to draw, what is the velocity vector of this bug? We know it's going to be some value, and you can see the length of each one of these are exactly the same, which means the speed is not changing. But what is changing is that direction of the arrow. So with that, what causes the direction of that arrow to change? Okay. It's something we call the acceleration. So in radial motion, there's an acceleration vector that always points inward to the axis of the rotation that moves this velocity vector so that it continually changes as it goes around. And that acceleration, we can determine that by using, this is a tangential velocity related to angular velocity. This is this is centripetal acceleration, A sub c. So centripetal acceleration related to angular velocity, omega squared r, or r omega squared. It's also equal to the tangential velocity divided by the radius. So these are just a couple of important formulas that we'll be using. Again, these arrows are vectors, right? They show direction and they show magnitude. And you'll notice that the centripetal acceleration also all have the same length, so their magnitude stays the same, but they continually change direction as it rotates around. And that's what affects the velocity vector. Okay, I have a small activity for you to do where you will look at how these velocity vectors act. Okay. What you will need is a laptop over here, a power cord, and an internet plug to plug it into wherever you see a star. You should have a good internet connection. And I have a password for you to get on, and I have a paper for you to use. Okay. You want to work together as pairs, is probably good. So why don't you get your teams together, come over and get your laptop, get you started. Quick quiz. This is easy. Based on your experience now with the ladybug, okay? 2 questions. 1, what would the acceleration and velocity vectors look like? Let's say this ladybug is going in the clockwise direction, okay? So which one of these would be correct for the acceleration and velocity vectors? Hold on a second. Is this right?
Yes.
Oh, okay. Does everyone have an idea?
Yes.
What's your idea?
C.
You agree with that? You agree with that? That's really good.
Good guess.
Now, well, could you have done it before you did the ladybug exercise? C. Very good. Okay. So one other question. If you had 2 bugs moving in a circle, or insects for you biology, oh, she left, good. She might say I shouldn't call it a bug. If you had 2 bugs moving in a circle like this, what would the velocity vectors at point X, here are the bugs, okay, now it's rotating around, it's rotating in this direction, so it's counterclockwise. What would the velocity vector at point X and point Y look like? And why? Remember, a vector, the length of the vector is the magnitude, right, the number, and the direction is the direction. So which answer do you like?
B.
Why?
Because the radius of the X is higher, is longer, so the magnitude will be.
That's right. Right. The further away you are from, what does this represent? Axis of rotation, right? The faster they're going to go individually, right? The further you are from the axis of rotation, the faster you're going to go. Okay, great job. Okay. Ta-da! See? Oh,
Why? I remember at Goddard they said something like where if something was out in space it goes slower. So the further
whoa,
away
whoa,
from Earth,
start over again. Something out in space goes
so
slow?
Not so much out in space, but the further away from Earth it goes, the slower it goes. There's something
That's rotating?
yeah.
I'm not sure you got the whole thing. I don't, it sounds like it's not couched in, there must be more to this.
I don't know. Maybe
No, he's saying that the planets that are further away orbit slower than. the
Okay,
planets that are closer.
I'm going to explain why that's different. This only occurs when things are linked together. These bugs are sitting on the CD, okay? There is not a link, there's not a physical link between Pluto and the sun and the Earth and the sun. So there's something a little bit different happening there. So it's only when you have a structural connection that they are rotating at the same angle axis. They're rotating around the same axis at the same angular speed. Okay, that's not occurring with the planets. The planets are like free bodies out there. Other things are having an impact on them. Okay, so that you're absolutely right. That's what they said. Mercury goes a lot faster around the sun than Saturn. Okay, you see the difference?
Oh yeah, I know. Yeah, I
Okay.
know the difference. I didn't know why that was slower.
Okay. Okay. I'm going to give you a break and not give you the next problem. I have a question for you. In your group, I've given you some cups. Can you, in your group, decide, take one cup out, okay? And I want you to just, don't blurt it out, just discuss, what's the axis of rotation of the cup? Okay. I'm just throwing that out to you. What's the axis of rotation of the cup? It's rotating. Where is the axis?
Out here.
Use your pen to show me. So it's rotating. Okay. Okay. So so she's saying that this is the axis, and the cup can
No,
rotate
not on the cup, it's away from the cup.
away from the cup. Okay. It's still rotating about an axis. Anyone else? Any other thoughts? That's good. That's fine. Any other thoughts? Okay. Here's another one. It's saying it's rotating about this axis. Okay. Anyone else? Both of them are good. You have an idea? Are you looking it up?
Thanks, cheated.
Okay. So we have an axis of rotation this way. We have an axis of rotation this way. Okay. Actually, they're both axes of rotation. Okay. So that's good. But we're going to use, which means an extended object, like a cup, can have more than one axis of rotation. Okay, and that's absolutely correct. I honestly, I never thought of that one, so that's a good one. That's great. What I'm going to ask you to do is we're going to use one specific axis of rotation, even though there could be more than one. Thank you. Let's use this one, the one where the axis goes through the bottom of the cup. Okay, so if you have that and you rotate it about that axis of rotation, what happens to the cup when you put it down and do that? And I've kind of already shown you it right here. Right? So it rotates, here's the axis, and it rotates. What happens? It goes in pretty much a circle. Okay. The reason it does that, all right, so here's the axis. A point right here is, I don't know, let me see. This is the axis there, right? So a point on the edge here is like 2.5 centimeters from the axis of rotation on this edge. A point on this edge is 3.5 centimeters from the axis. So a point here is closer to the axis than over here. So which one goes faster? The point here or the point here? Point on the outside. And since it's going faster, it can cover more distance, right? It's covering more distance in the same period of time as in here, okay? If this is where the axis is. Okay, so the inner edge of the cup, I'm calling this the inner edge, closest to the axis, moves slower because it has a shorter rate, it has a shorter R, right? It's your beetle up here as opposed to your beetle over there, right? This guy was going slower than this guy. Then the outer edge of the cup, the outer edge covers more distance per rotation. Okay. Each group is going to need 2 of these and a few books to make a little inclined plane. You need to take your 2 cups and put them together like this with some tape. Now, what I didn't realize when I bought these cups is that they're waxed. So when I first tried to put them together, I had trouble with the Scotch tape wouldn't stick, you know. So I guess I have some masking tape. So you want 2 sets of cups, one that looks like this and one that looks like that. You each need 2 rulers and a couple of set of books like that. And I want to see, after you put your cups together, I want you to roll them down the rulers, okay, to see which one is stable and which one is not stable. And then we'll talk about why one is stable in rolling down the rulers and one is not. Okay, you make a little inclined plane with 2 rulers. So don't destroy your cups. I would like to use them for the next group. Maybe I'll unpeel them. What did you find about the cups? Obviously the 2 cups, they both of them had, excuse me, they both have the same mass, basically, right? You took 2 equal cups, put about the same amount of tape on them, so you have the same mass here. What was the difference between them when you tried to roll them down your inclined plane? What happened? What was your experience? This one, okay, show which one? That one wobbled. Did it make it all the way down? Sometimes they did. Mostly it didn't, though. It would fall off pretty quick. What about the other one? Did the other one make it all the way down? Yes. Okay, what do you think was happening? There was some discussion here that it was good. You want to share it?
When we have this one here, the mass of this one is more centered. And the velocity also, because the radius here is higher, longer or wider. So it stays centered.
Okay.
But on this one here, the mass is like more dispersed.
Okay, so how the mass was structured on the cup may have had an impact. And in fact, what you experienced is exactly how railroads run on tracks. If you ever look at the railroad wheels, I don't think you ever got that close to it, but they work something like this. You know, the tracks, there's nothing on the track clamping the wheels on, okay? But the wheels themselves are tapered, just like this is tapered, right? So what happens is, and this is how the railroad wheels stay on the track. It has nothing to do with anything holding them on. What happens is, if you're on a railroad car and it goes like this, right? As you're going, it begins to sway a little bit one way or the other. Maybe if you're taking a car and it sways a little. Do you ever anyone go on a railroad at all? Do you ever get that feeling? Okay, what's happening is exactly what happens when this was rolling down. It might have gone one way, but then it comes back. It comes back. It's self-correcting itself. Why? Because if the wheels go a little bit too far this way to the right, it begins to run on the narrow part. okay? The narrow, this is the axis of rotation here. So this side is closer to the axis of rotation than this side. This side is further away. So which goes faster? What's the fastest velocity? In here or over here?
What?
The faster velocity. Right, because it's further from the axis of rotation, just like the ladybug on the outside of the CD was moving faster. Okay? So what happens is when the cars shift a little bit to this side, let's say, okay, this wheel is going faster because it's now resting further out from the axis of rotation than this wheel. This wheel is going slower because it's closer to the axis of rotation. Okay? So if this is the axis of rotation right here, right, this R is smaller than that R by that amount. Okay? So this is going slower. This is going faster. So the narrow part of the wheel goes slower. It's going slower, and it causes it to curve, and it self-corrects back. Right? When it goes the other way, the wide part of the wheel goes faster, so then the wheels turn to the right. So it's self-correcting itself, and that's why these wheels here look just like this. And that's why this was able to stay on your little inclined plane, and this one had no stability at all. It basically fell off because it was opposite of what was happening here. Okay. And everything, it's really revolving around, I like the idea about mass, and we're going to talk about that. Might have had a little thing to do with it. The whole idea is that when something is rotating, obviously both the wheels are rotating at the same angle of velocity. Would you agree with that? Same W, the same omega. But every point on the wheel has a different velocity, just like your bug on the outside of the CD was going faster than your bug on the inside. Okay? So that's the concept of rotational motion and linear motion, and one example of how it operates in real life. Okay? So wheels stay on the track during turns. See, the narrow rim moves slower. The narrow rim, this part here, moves slower because it's closer to the axis of rotation of the wheel. The wider part, and it doesn't take a whole lot of difference, the wider part moves faster because it is further from the axis of rotation. And that combined motion, you get that little bit of that wobbly feeling sometime when you're sitting in the chair, on the bench on the train, but that's what's happening. The wheels are self-correcting. And there's nothing holding them onto the rail. Nothing holding them on there. They're just sitting there going. Of course, I guess if the rails move, you're in trouble, right? I guess that's the idea. Okay, any questions? Okay, so let's take this one step further. It's related to the mass. And let me start by mentioning that those of you who were with me in previous years, I talked a little bit about Newton's laws, first, second, and third law. And his first law of linear motion, I'm going just stepping back and then we're going to apply it to rotational motion. Newton's first law of motion also is called the law of inertia. Okay. If there's no forces acting on an object, then its speed and direction of motion do not change. In real life, there are many forces that act on an object. If I push this chair, it should continue to go on forever. The reason it doesn't is that other forces are acting on it, namely friction. Okay? So it stops. But if there were no forces, it would keep going forever. So objects keep doing what they do. This is Newton's first law. If an object is at rest, it stays at rest. If it's in motion, it continues in constant motion, not accelerating, all right, in a straight line with the same speed. So that's in terms of linear motion. How do we apply it to rotational motion? Okay. All right. Oh, we call it the law of inertia, first of all, because inertia tells us something about the mass of an object. Something that has a small mass has a small inertia. It's very easy to begin to move. Something that is a large mass, has large inertia, it takes a lot of force to get it moving, and it takes a lot of force to stop it. So in terms of linear motion, it looks something like this, right? A railroad car is very heavy, it has a lot of mass. This is a lot of inertia. It takes, these things don't start off at high speeds, takes a lot of torque to get the wheels moving, and eventually it gets moving. And on the other hand, it takes a lot to stop it once it gets moving. Okay, so a large mass resists changing its motion. It's either going to sit there or it's going to keep going at a constant speed. Difficult to stop when there's a car in the track, and you know what happens in that situation. When you have a small mass, it is very little inertia, right, and little resistance to getting it going or stopping it. Right? So we measure inertia, we measure it with mass, right? How many kilograms. This is linear motion, things going in a straight line, things going up and down. But what happens when we're talking about rotational motion? The inertia of the Earth moving around its axis. The inertia of the CD as you begin to spin it up around its axis of rotation. Okay. Inertia is a measure of resistance to motion. Is probably the simplest definition. Well, what's your definition?
Basically wanting to stay immobile, like just stay.
Yes, okay, stay immobile, or if you're moving at a constant velocity, not changing the velocity. So it's one or the other.
So not wanting a change in speed, like if that
Not
train
changing, not changing.
like if that train is moving, that movement is inertia.
Inertia is measured in this case in mass. So this has a lot of inertia because it has many kilograms of mass. This has a small amount of inertia. Okay, so inertia is the mass of an object. When it has a lot of inertia, it resists changes in motion, which means it's hard to get it started and it's hard to stop it when it is moving. Very small mass, small inertia, easy to get it moving. Is that about what you're thinking?
It is now.
Okay. Applying it to anything that's rotating, we have something that now we call rotational inertia. It's like we had rotational velocity, rotational acceleration. Now we have rotational inertia. And using that idea of difficulty of moving something or stopping something, an object rotating about an axis tends to remain rotating about the axis unless interfered by some external force, friction. Right? And once you get an object rotating, it's hard to stop it, particularly if it has a large mass. Okay. The property of an object to resist changes in its rotation, rotational state of motion, is called rotational inertia. Okay. This very much depends on two things. One is not only the mass, large train, small carriage, but also the axis of rotation that we're moving that mass. And we've had a couple of ideas of axis of rotation around the cup. Right? We had the cup going this way, and then we had the cup going this way. Your pen. Each group take a pen and figure out what the axis of rotation is for your pen. And I need a volunteer. Are you volunteering? Okay. How many axes of rotations did you find with your pen? Okay, what are they? You have one? Which one do you have? What's your axis of rotation?
X direction.
And how does it rotate?
In
Okay, did everyone see that? Okay, so use this as a pen. Can you demonstrate which axis of rotation? Okay, so where's the axis?
Where's the axis?
Yeah, where's the axis?
Right, I don't know, right in the center.
Okay,
From the
right.
side.
So the one is, here's the axis of and rotation was which way? Like that. Okay, that's one. What other axis of rotations do you have? Okay, we have another one here. Where's the axis?
In the center.
In the center, and you can rotate it? Okay. How about another one?
Or up and down the length of it.
Up and down, show me where it is, and then show me a rotation.
Well, I mean, it's the same action, but you can rotate it around the center instead.
Yeah.
Or
Okay.
one end, but not
This way?
at the end, or
That would be
like if you
a
hold
Z
it.
Okay, you're rotating it through a central axis like you did before.
Yeah, it's the
Sure,
same
do it.
thing.
She wants you to do it a different
Do
way.
it just from here, to
From
your
here?
right hand.
Yeah.
Yeah.
All right, so,
Oh.
okay, it's rotating about an axis, right? Here's the axis, right? Okay, now the question is, without hitting me, the question is, did you find any difference in motion as you were doing this? Was there some ways easier than other ways?
Well, yeah,
Which one was the easiest for you?
this,
Okay, so that was the easiest, all right. And what was the hardest, or the most difficult? Over there,
if the axis is off the center.
okay,
More difficult.
okay. Now,
I won't get that yet.
has the mass of this changed during this little demonstration? No, so the mass is the same, okay. But you did have some difficulty rotating it on certain axes. Axes? Axes. Okay. All right, thank you. Just, you can put that there. So we found there could be more axes of rotation, but here's an example of 3. One of rotating the pen or the object around this axis. One was rotating it around this axis. And the most difficult was rotating around this axis, right? Even though the mass stayed the same, there was additional difficulty depending on the axis that you were rotating. So through which axis is the most difficult? It was this one, right? You had trouble with that one. Okay. So, did I just flip it? Oh, it says the same thing, huh? So the ease of rotation depended on which axis you selected, okay, and how that mass was distributed around that axis. Okay. So for rotational inertia, rotational inertia depends the mass of the object, as did linear motion, mass of the object, but also the distribution of the mass around the axis of rotation. And you found that with the cups. You suggested that with the cups, that had some play into it. All right. And anyone who has worked with, did you ever work with these at the Y? Okay, so I don't know if you can move the weights on them in and out. I think they're pretty much set. But which one would be easier for you to rotate, this one or this one in your hand? This one up here, right? Even though it has the same mass, the distribution of the mass is different, and this one would give you less resistance to changing its moment, to rotating it. So the greater the distance between an object's mass, concentration, and the axis, the greater the rotational inertia. It's like giving it more mass almost, the greater rotational inertia. Okay, I need another volunteer. Huh? I need a volunteer. Come on. I need someone to try this out and give us their opinion. Try not to drop it on the floor. Let me stand aside. Okay, you know what you're going to do, right? You're going to try to balance it.
Oh, I'm
And then you're
horrible
gonna-
at this.
Huh?
I'm horrible at this kind of thing.
Let me hold it.
Use 2 fingers. 2 fingers?
No, one finger.
Ah, I'm not good at this.
Okay.
There we go.
All right, now how about the other way? Oops.
Almost took your toe.
This might not be the best hammer to do this with.
The head isn't heavy enough.
Flip it over again. Which one is she better at, actually?
The wrong way.
This way? How many feel that
This
she?
is really light.
It's very light. That's the problem. I had one at home I wanted to bring in, but I was afraid it would make a ding in the floor when I fell. Which way do you feel was easier for you to balance?
Probably this way.
This way, okay. In a way, it's counterintuitive, doesn't it? Because most of the weight is up here. As you observed her, which way do you feel she had better this way? Why? It's the same mass, right? I haven't changed she didn't change the mass. The only thing she changed is what? What? Well, we haven't talked, what did she change? Where was the axis of rotation? Good, that's good. But where was the axis of rotation for for this hammer? The finger was the axis of rotation, okay? Where was the distribution of mass, depending on which way she had it? All right, where is most of the mass now?
The head's
How? Most of the mass is, so you would think it'd be easier this way, wouldn't you? Why was it easier this way?
Because it's harder to change the momentum when it's.
It was harder. It's more difficult to change rotational inertia when the mass is further away from the axis of rotation.
Oh, wow, that's so bizarre.
Okay? So, all right. Same mass. Same mass. Smaller moment of inertia this way because the mass is near the axis of rotation. Larger moment of inertia. And what did I say? The greater the moment of inertia, the less opportunity you're going to have for rotation. So it was a little bit easier this way for you. Again, a little bit counterintuitive, but this has the greater moment of inertia because most of the mass is further from the axis of rotation. And if it has a greater moment, it's like saying it has more mass. It's going to resist change. And she's able to compensate that because it's resisting change. And she can move her finger fast. Once you get a little bit experience, you can balance it a little bit easier. So that's why it's easier to balance this way than this way. Okay, one more. How about another volunteer? This one will require no hammers. Another volunteer. Here it is. Another volunteer. Come on. Do I have to pick someone? Okay. 2-meter sticks, right? And what I'm going to ask you to do is just, maybe start them at an angle. Whoops. Didn't mean to do that. I'm looking for a flat wall. It's not really flat here. We start them at both at the same angle like this, and I'm going to ask you to let them go. Don't do it yet.
Okay.
Okay.
Do you want them on the other side of me or does that matter?
Either way, but you can put it next to each other if you like, because that way you can see that they said it's the same. And keep them a little higher, yeah. And make sure they're both going to start. They're both going to start from the same distance from the ground. There you go. And hopefully she'll let them go at the same time. Now the question for you is, I hope they'll be okay there. I had to do it against the wall before. You want to do it against that wall over there?
Sure.
That way it'll be up against the wall. Which one hits the ground first? Let's think about it.
No, wait.
Which one and why? Which one do you think is going to hit the ground first and why? Obviously there's more mass on this one. Right? Oh, by the way, in case you can't see, I put a couple of, I think it's at 200 grams on there. There's 2 of them.
There's tape on there.
I think it's like 200-gram weights. And they might fall off because the first time I did it, they all broke and fell off. Okay, so which one will hit the ground first? The one with the weights or the one without the weight? And why?
Without.
The one without the weight and why?
Well, I know that if I had a hammer in my hand and I wanted to flip it like this, I know that if I held it by the hammer, like the one on the right, it's going to rotate much slower than if I try to flip it in my hand holding the head of the hammer. So I just
Great, that's
use that to explain
great
that.
description. So we're talking about rotation. So when she lets go, where is the axis of rotation of these things? At the floor, right? It's going to rotate about the floor. Okay. And in terms of the hammers, which one is which one now? This one is the one with the weight on the top. And you're saying that that rotates less. And the reason it rotates less is because its moment of inertia is greater. Okay, you ready? So when we say, when you feel like you're ready, you can let it go and someone watch and observe which one hits the floor first. Which one hit the floor first? Could you tell? You couldn't tell. Do it again. No way. And the reason is, thank you very much, the other one had a greater moment of inertia. It rotates less fast. Thank you very much. Good job. Okay? So, this is the idea. Which stick had the greater moment of inertia about its bottom end? They said to use Play-Doh, but I didn't have any Play-Doh or clay to stick on it, so I just threw on a couple of weights. Which stick rotates first? This one rotates first because its moment of inertia is less. This one resists changes, right? It's stationary. It resists changes in motion. The force acting on it is gravity once you let it go. It resists changes in motion and therefore rotates more slowly than this stick here. So, rotational inertia. The greater the rotational inertia of an object, the harder it is to change its rotational state. We've been starting with stationary here. We started with stationary with the hammer, and then we began to rotate it. And that's exactly how, did anyone see that guy go across the Grand Canyon? What's his name? Walinda?
Walindas?
The Walindas. Right? That was really, right? He did use a stick, right? He used a stick. I heard him interviewed the other day on NPR, and the interview was an interview conducted before he went on this trek across the Grand Canyon. And he was asked a question about what kinds of things have happened to him. He's actually done this kind of stuff, like birds have landed on him. Birds have landed on his stick. Oh, so anyways, that could change his moment of inertia. So a tightrope walker carries a long pole that has a high rotational inertia, right? So unlikely to change, right? It wants to stay stationary. So it does not easily rotate, and it keeps the person very stable. So this idea of rotational inertia, rotational inertia, sigh, right? He's very happy about that.
So can we then assume that those poles are weighted at the ends?
They are. And in fact, I don't know what they are, but I did read that they are weighted on the ends, which will help them also. It increases the rotational inertia. Okay, now you all know that, right? Okay. So, just to kind of quantify it a little bit, all right, we've been doing things. So then I'm going to stop because the next thing I'll do, I'll have you apply it when I meet you tomorrow, and I'm going to give you some information about your projects. But, right, this is some example of rotational inertia and how we quantify it. And for example, first of all, when I talk about, whoops, what did I just do? When I talk about, mass in terms of motion, I call it M. M is for mass. And the units that we use are kilograms, right? When we talk about mass times velocity for momentum or kinetic energy is 1/2 mv squared and so forth. In rotation, we don't talk about mass, we talk about moment of inertia, I, or rotational inertia. All right, so this is rotational inertia, or moment of inertia. And look, it involves not only mass, but the distance that the distance to the axis of rotation, r. Okay. So moment of inertia, or I, the actual units are kilograms meter square. And that meters represents the radius. And here's some examples. This is something you look up. There are charts of these depending on, and we use symmetry a lot, right? The moment of inertia of this cup is much more difficult to determine because it doesn't have a whole lot of symmetry. But we'll start simple. So take a look at this hoop. This hoop is the same as that hoop. They have the exact same masses. But look at the axis of rotation. This hoop, right, is rotating this way. Oh, here's a hoop. Here's a hoop. Okay? This first hoop is rotating through an axis like this. Okay? That's one axis of rotation. So it would be its mass times r squared, and r would be the distance from the axis to the edge of the hoop. Okay? If I change the axis of rotation of this hoop, so it rotates like this, right? Axis like this, the moment of inertia has changed. It's now 1/2 mr squared. So you have to know not only the mass and the shape, but what axis you're talking about. Just as the axis of rotation of this was much more demonstrated than by your pen, which is easy to move. It's easy to rotate it through the axis this way because its moment of inertia actually is quite small. More difficult to rotate it this way where the axis is in the middle, and much more difficult to rotate it this way where the axis is on the end. So look here, here's a stick. Let's say I rotate it this way. Its calculated moment of inertia I is 1/12 ml squared. Well, they take L as the whole length here. 1/12. I take the same thing and I try to rotate it about here, right? Its moment of inertia is 1/3 ml squared. So obviously, this is a smaller moment of inertia. It's a lot easier to rotate. Larger moment of inertia, more difficult to rotate. Okay. We're going to try some experiments tomorrow, well, kind of demos, because I don't have a whole lot for everything, about different types of moments of inertia and how it changes the motion of different objects. Okay. But you can see the different, how one calculates this I, this moment of inertia. How do they come up with it? I have no idea.
I mean, it just
It's
seems
well, it's
weird. Yeah, I mean, it doesn't.
yeah.
It's so different.
Someone thought of it. I don't know who thought of it.